To apply Bayes' theorem to DNA identification of mixtures, it would be good to have a simple example of how we infer genotypes and from those construct likelihood ratios. A very good example is inclusion, which we will use here. Next slide. We begin by looking at mixture data. On the top left, we see some amount of contributor A's genotype at a locus. The x-axis here represents the length of an allele. So the two blue bars that are shown vertically show a certain amount of two alleles of smaller length. Underneath it, we see another axis where there are two orange alleles representing another amount of contributor B's genotype at a locus. When those are put together in one tube, then you have more of contributor A than you do of contributor B. When they're amplified in the polymerase chain reaction on the right, we see the end result, which is mixture data that we can observe that has genotypes containing contributors A and B with the alleles of blue shown on the left in greater amount and the alleles of A in smaller amount shown on the right. And next slide. These expectations of the different amounts of contributors and what their alleles would be are reflected in quantitative data shown here in green. Now, a quantitative likelihood function is one shown here in gray that tries to model and account for and explain what the quantitative peaks are based on selecting different allele pairs for the genotypes along with other parameters such as mixture weight, quantity of DNA, stutter, and so on. We will be returning to this later on. Next slide. Imagine, however, that we had some sort of qualitative DNA assay that could reliably give us the alleles that were contained in the data. So this is not looking at quantitative peaks in any way. One could imagine that sometimes a threshold procedure could do this, but we are trying to detect only the presence or absence of alleles. This might be done using a hybridization assay, for example, where there would be very high certainty for larger amounts of DNA in a mixture as to whether or not the alleles were present or absent. Here we see represented in 4 blue vertical bars that a determination might be made using such an assay that qualitatively 4 alleles were present and no other alleles were. Next slide. Let's focus as a simple example on a case where there would only be 2 alleles that were detected, and we're trying to understand how to infer genotypes, which are probability distributions of allele pairs, from such data. We begin by looking at what occurs in the population. Here's a Punnett Square, which, as you know, represents the probability of different allele pair combinations in genetics. We're focused on the 2 alleles, 1 and 2, and yellow represents the other alleles that we're not talking about right now. Suppose that the probability of seeing allele 1 in the population is p sub 1, and that the probability of seeing allele 2 in the population is p sub 2, and so on for the other alleles. Then the probability of an individual having allele pair 1, 1 would be p1 squared, as shown in the blue. And similarly, for the homozygote allele pair 2, 2, that value is shown in red as p2 squared. Now for heterozygote values, 1, 2, those can be inherited in 2 different ways depending on the ordering of the parents, and those are shown here in purple. So there are 2 ways of having P1, P2 for a total of 2 times P1, P2. Next slide. Rearranging these allele pair probabilities onto an axis of allele pairs, we list out the allele pairs 1, 1, 1, 2, 2, 2, and so on for all the other possible allele pairs, and assembling the probability from the Punnett square we just saw, the homozygote square in blue for allele pair 1, 1 is p1 squared. For the heterozygote, we combine and stack up the two purple bars, each with probability p1, p2, giving us 2p1, p2 for allele pair 1, 2. And for the homozygote allele pair 2, 2, we have the quantity p2 squared shown here in red. This bar chart of allele pair probabilities represents the prior probability that we have from the population of what we believe the genotype would be of an individual before we see any of the evidence mixture data. Next slide. By Bayes' theorem, in addition to having a prior belief before there's data, we also need to know what to do with the data once we have it, and how different hypotheses of allele pairs can explain the data, and that's taken care of by the likelihood function. The inclusion likelihood rule says that both of the alleles of a candidate allele pair must be included in the mixture evidence in order for it to be assigned some likelihood. So, for example, if the mixture evidence contains just the two alleles 1 and 2, then only the allele pairs 1, 1, 1, 2, and 2, 2 have both of their alleles contained in the evidence alleles. Every other allele pair would include some allele, say 3, 4, 5, that is not in the evidence and therefore would be excluded. This likelihood function assigns a relative likelihood value of 1 to the included allele pairs and a relative likelihood value of 0 to those that are excluded. This all or none approach is equivalent to creating a list of the included allele pairs, 1, 1, 1, 2, and 2, 2. Next slide. Here in a table, we summarize where we are so far in inferring our genotype, the probability distribution over allele pairs, using the inclusion likelihood function. In the first column, we simply list the allele pairs. We group them by those that are included. Suppose that alleles 1, 2, 3, and so on, up through k, are included, and the remainder of the alleles do not appear in the mixture data. Then those corresponding allele pairs containing an allele not in the included evidence alleles 1 through k would be excluded. In the second column, we see the prior probability from the population. This is simply taken from the Punnett square that we saw, where homozygote allele pairs are given a prior probability of pi squared, and heterozygote allele pairs are given a prior probability of 2pi pj, where I and j correspond to two different alleles. You might notice that these prior probabilities over all possible allele pairs do add up to 1. It's a probability distribution. Now, in the third column, we move to the likelihood function. This is the inclusion likelihood function. It says that every allele pair who has both of its alleles contained in the evidence data is assigned a number of 1, and anything that's excluded that has some allele in its allele pair that's not in the evidence list of alleles 1 through k is assigned the number 0. The likelihood value is completely arbitrary since it will divide out between the numerator and the denominator. We could have chosen a likelihood value of 100 in 0 or half in 0. It's easiest to use 1 in 0 to represent either being listed on the included allele pair list or not being listed. The fourth column is the product of the likelihood and the prior. And here, which you can easily do on a spreadsheet, we multiply together column 2, which is the prior, times column 3, which is the likelihood. Multiplying them together, we essentially select out those included allele pairs, multiplying them by 1, and zero out the excluded allele pairs. So now we have the product p1 squared, 2p1, p2, and so on, with those allele pairs that are excluded receiving a probability of 0. Now, if there are more than 2 alleles in our example, or k in this table, then we're going to be getting rid of some probability mass from allele pairs. Therefore, the sum will not add up to 1, and this will not be a probability distribution, which is what our goal is going to be in the last column. To take care of that, we simply need to find the normalizing constant that appears in the denominator of Bayes' theorem, so we can divide by the right number and make the probabilities of each included allele pair add up to 1. Well, summing up these numbers, p1 squared plus 2p1, p2, and so on, we see at the bottom of the product column the sum appearing, p1 squared plus 2p1 plus p2 plus ... plus pk squared. Rearranging terms, we arrive at the sum p1 plus p2 plus ... plus p sub k, each of the allele frequencies of each of the included alleles, quantity squared. In other words, what we're looking at is the standard inclusion probability. Well, moving over to the last column for the posterior probability, all we do, following Bayes' theorem, is we divide each product value of the prior and the likelihood for that allele pair by the normalizing constant, which here we see is the inclusion probability. Since the inclusion probability is less than 1, this has the effect of stretching up that product value to a larger number. And it stretches it by just the right amount that when you add all the numbers together that have been rescaled by the small denominator, we see at the bottom of the final column that we do have a probability distribution, and these numbers are the posterior probabilities of the inferred genotype using the inclusion likelihood that adds up to 1. Next slide. Here's a picture of that posterior probability. We now have 3 bars in this bar chart, and the mass of these bars adds up to 1 to give us a probability distribution. Notice that the relative probabilities here of each of the included allele pairs is proportional to the prior. All that's happened is a stretching, increasing the likelihood times prior values up to a final posterior probability for each genotype allele pair value such that the sum over all of the probabilities equals 1. Next slide. From this genotype probability distribution, which we call Q for the questioned evidence, we can compute a likelihood ratio. There are many ways to compute a likelihood ratio. They all give the same number, but the calculations can be done in different ways depending on whatever is most convenient. Here, what is most convenient is to observe the ratio of the posterior probability, Q, at some allele pair little x, divided by the prior probability, which we call R for the random reference population, evaluated at the same allele pair value, x. For most match statistics, one can imagine that x, the allele pair value, corresponds to the suspect. So let's assume that allele pair little x is the allele pair of an included suspect, and let's calculate the likelihood ratio. What was the gain in probability at the suspect's allele pair? Well, in the denominator, we have the prior value, the population frequency, R of x, and in the numerator, Q, the questioned evidence posterior probability, is simply that same prior value, R of allele pair x, divided by the normalizing constant, which is the sum of the allele frequencies that were in the mixture data squared. Most importantly, that means that the prior probability R of x in the numerator and the denominator cancel. So moving on to the third line, we're left with 1 over the sum of the allele frequencies of the included alleles squared. Well, this is nothing more than 1 over the inclusion probability. So by using an inclusion likelihood as the one of many possible ways of explaining the data, in this case by inclusion, we have shown that when you infer a evidence genotype using Bayes' theorem, here called Q of x, and you form the likelihood ratio, what you obtain is 1 over the inclusion probability, meaning that inclusion is itself a likelihood ratio. Next slide. So we see that with mixture data, which is uncertain, with alleles placed in various places, and often having more than 2 alleles, we infer uncertain genotypes from such uncertain data. And our mechanism is using Bayes' theorem to update our probability. We begin with a prior probability on each possible allele pair of a contributor at a locus, corresponding to the population probability. Before we see the mixture evidence data, that represents our belief about the evidence genotype. Now we see data, mixture data in this case. And in order to update our beliefs, we form a likelihood function. In the previous example, we used an inclusion likelihood function, which is the simplest and weakest of all possible mixture likelihoods. And combining the data, as explained through the likelihood function, together with our prior beliefs, we arrive at the posterior probability, which reflects our updated beliefs that the data now tells us where to concentrate our belief in different allele pairs. And then we also saw that by taking a ratio of the posterior probability to the prior probability, that this forms a likelihood ratio. So the concentration of probability as given to us from the data and expressed through the likelihood function, when combined with Bayes' theorem with the prior, concentrates the probability in places that may or may not correspond to where the suspect genotype would be. Next slide. Let's take a look at some examples visually. Here is a uniform population prior on a 3-allele locus system. Again, I'm using a smaller number of alleles to keep the examples simple and more visually apparent. The 3 possible alleles give us 6 possible allele pairs. Now, before we actually use an STR locus, we do population studies. Next slide. And from these allele counts, we come up with a more realistic population prior of what we believe the various allele pair genotype candidates would be before we see the data. So we'll use a realistic population prior as we do in regular forensics. Next slide. Let's consider several different likelihood functions. First, let's take the inclusion function, which says that all included allele pairs are given equal weight. So here, the allele pairs 1, 1, 1, 2, and 2, 2, which might represent the first 3 out of the 6 possible allele pairs, are given equal weight, and they would be put onto a list, as opposed to the other allele pairs that might include allele 3 and would not make it onto the list. Next slide. Other methods, such as obligate allele methods that consider the victim, or quantitative methods that rule out possibilities based on peak heights, filter this list of all possible allele pairs, and so their likelihood functions have fewer candidate allele pairs for the inferred evidence genotype on that allele list. So here we see perhaps one of the candidates has been removed, and we're left with 2, each given a higher likelihood, and the allele pair that has been removed from the list is given no likelihood at all. Next slide. One can also use quantitative methods that make use of peak heights, such as statistical computer interpretation. And now we no longer have a list of equally weighted allele pairs, but now the weighting of those allele pairs is determined by the data and are no longer the same. Next slide. Let's go through some examples with these three likelihood functions and see where we get, starting with the same prior probability. Next slide. Let's combine the prior probability with the inclusion method, an equal listing of all pairs of probability. So the three priors on the left will be multiplied by an equal weighting, whereas the three allele pairs on the right will be eliminated. Next slide. And in the posterior probability, we see the result of that multiplication followed by dividing by the inclusion probability to renormalize to 1. The result is the posterior probability distribution shown in blue. At the first three allele pairs, there's positive probability. At the last three allele pairs, there's none. If we look at the ratio of the posterior, shown in blue, to its neighboring prior on the left, shown in brown, we see roughly a twofold gain in probability. This represents the likelihood ratio or the information increase. So suppose, for example, that it's the first allele pair, shown here listed as 1, that corresponds to the suspect. When that allele pair is selected out and we look at the ratio of probability of the blue bar to the brown bar, we'll see a likelihood ratio of 2, which is the information contained in the data for that match. Next slide. Let's start with the population prior again, next slide, but this time let's use a different likelihood function. Let's use something more informative than inclusion that maybe eliminated one of the allele pairs from the list of possible allele pairs at that locus. There's more probability concentrated now on the first two allele pair candidates on the left and none at all on the 4 allele pair candidates to the right. Next slide. The result is that with Bayes' theorem, multiplying the prior brown probability distribution by the green likelihood function, we arrive at the blue posterior probability. What you might notice is that this concentration of probability is now more focused on the first two allele pair candidates, and there's an increase. Because it's a list-based method, we still have equal likelihoods, and therefore the two blue bars in their probability are proportional to their prior probabilities shown in brown. You can see that parallel of the heights of probabilities. Here, however, there's been a fourfold gain in probability going from the prior in brown to the posterior in blue, and that corresponds to a likelihood ratio of 4, which is more information than what we had with the inclusion method. Next slide. We'll do this one more time. Here we start again with the population genotype prior. It's always whatever we believe the population would be. Next slide. But now we'll use a quantitative likelihood function, where after looking at the quantitative data, it focuses more of its probability on the first allele pair candidate than on the second allele pair candidate. When we use Bayes' theorem and multiply the prior, shown in brown, with the likelihood, shown in green, next slide, we arrive at the evidence genotypes posterior distribution, shown here in blue. Notice how the blue probability bars for the first two allele pairs are no longer proportional to their prior probabilities shown in brown. This is because we're not using a list-based method, but we're using all of the available quantitative data. If the suspect had the first allele pair, then the likelihood ratio here would be the ratio of the height, the probability of the blue bar, the evidence genotype posterior value at that allele pair, divided by the brown bar on its left, which is the prior genotype probability. And we see that the ratio is about 8 to 1. So in this way, by preserving more of the information present in the quantitative data, a more informative likelihood function can achieve a greater likelihood ratio to express that information. Next slide. Let's summarize some conclusions. First, we see that the inclusion method can be inferred as a genotype and represented as a likelihood ratio, just like any other genotype inference method. Therefore, there's really no controversy about inclusion versus likelihood ratio. They are the same beast. They just have different likelihood functions where inclusion tends to be the weakest. Also, we see that all uncertain genotypes are probability distributions, as they must be, since in science we have only one way of representing our uncertainty mathematically, and that's with probability. We saw different ways of preserving identification information by using more informative likelihood functions. We can measure the efficacy of how well information was preserved by looking at the logarithm of the likelihood ratio, which is a standard information measure. Moreover, we can apply that information measure to the inclusion method to analyze how effective or weak that inclusion method might be. By showing that inclusion is a likelihood ratio, we've given it more justification for its use in court, since likelihood ratios are always accepted in court. Also, the inclusion statistic can be understandable through its inclusion likelihood function. It's not just a formula where you put in some allele pairs and testify to it. It can be constructed like any other valid genotype probability distribution. So what's the relevance of the inclusion method? It depends on the data. If the mixture data are very easy and informative, and you end up with a high match statistic, it may be all you need. But in situations where more depth is required to interrogate the mixture data in order to arrive at a more informative genotype, and by extension, when you compare with a suspect in a population, a more informative likelihood ratio, then you might need to move beyond the inclusion method to more quantitative approaches. Thank you.